Hello, people on Zoom. Apologies. Where was I? Oh, yes. So what you see in the bottom plot here is model simulations that include the ocean model, looking at the subsurface dynamics, and in particular, the subsurface heat trend in decades where the surface is not warming, what we call hiatus decades. And what I want to highlight is that you can have, can we see this? Yes, we can have a surface temperature that's pretty low, where you have those blue patches, meaning that looking at global mean sea surface temperature, people might say, oh, has the warming stopped? But what's actually happening is that you have decadal variability in the ocean and climate modes that lead to a lot of heat being stored in the subsurface. And then in subsequent years, you might have release of this subsurface heat, and therefore you're warming, your signal in terms of sea surface temperature might warm again. So my main point here is that when we think about the climate system and ocean dynamics, really those subsurface dynamics matter. And we can't just think about sea surface temperature as the only signal that matters to the climate. Other examples of why we should care about ocean dynamics. The ocean provides heat for hurricane intensification. That's okay. Okay. And so here you see the path of the sea surface temperature after a hurricane has gone through. And what I want you to see is that, okay, the ocean does provide heat for hurricane intensification, but you also have a signal in the ocean of this cold wake where you have this blue shadow where the hurricane went. And so then subsurface ocean dynamics matter as to, okay, what happens to this cold wake? Are future events impacted by it? How quickly do we restore this heat reservoir for the next hurricane? The last point here is that in terms of global sea level, the terms that matter most are terms of adding water to the ocean by melting of land ice, and the heating of the ocean, which increases the volume. But in terms of regional coastal sea level, local dynamical changes to the ocean and certain climate modes like ENSO in the short term or like AMOC in the long term can really have a big signal in terms of local coastal sea level. So in this talk, again, we're talking about ocean modeling within the context of E3SM. And we're going to be focusing on the ocean model. We're going to go through some kind of fundamentals, the equations, mesh and discretization of en-pass ocean. Some practicalities, maybe the more subtle art of ocean modeling, where we talk about parameterizations, validations, some of the things, some of the key points I want you to learn. And we're going to end back into the coupled climate model, thinking a little bit about the connection and fluxes to other components. All right, so we're going to start with kind of big picture. How does ocean modeling differ from the atmospheric modeling, especially if some of you are atmospheric modelers?
And we had such a great introduction to atmospheric modeling yesterday. I thought I'd just point out what the differences are that ocean modelers think about and have to take into account when we write our ocean models. So a big one is that the ocean's incompressible, so divergence of U equals 0. I think of each column of my ocean model like a tube of toothpaste, right? If it comes in one way, it has to go out the other. We have land boundaries, so we have to think about our boundary conditions against the land, and of course that sets the whole ocean global circulation in a way that's completely different from the atmosphere. Our important tracers are temperature and salinity because that determines the density in the equation of state. Our equation of state is empirical, so the kind of subroutines and calculations that we're doing for the equation of state, for example, is typically a complicated polynomial from observations. So to say the obvious, the atmosphere is transparent, and the ocean is opaque. So what happens? The ocean is heated at the top and the atmosphere is heated at the bottom. And so in atmospheric modeling, you're dealing with a lot of convection, and the ocean is extremely stable by comparison. And so the way that what happens in the ocean is that your vertical motions are extremely weak, and the ocean's very stratified. And once you discretize the ocean, any vertical mixing is typically too high. It's caused by your numerics. So we spend a lot of time trying to minimize our vertical mixing in order to get similar values to the real ocean. Our current speeds are much less, and we don't have to worry about clouds and radiation. And actually, the reason that ocean modeling started at Los Alamos is there were computational fluids people there. This is in the 80s. And they said, oh, clouds and radiation is too complicated. We'll let NCAR take care of that. We can do fluid dynamics. We'll do the ocean. So that's how we ended up with the pop ocean model. But we do have to worry about mixing processes, which we'll talk about parameterizations for that in a few minutes, and freezing to form sea ice and frazzle. All right, the equations. We saw a version of this yesterday for the atmosphere. And so I always like to label all my terms. And so really everything is an advection diffusion equation, right? And then the momentum, F equals ma, you add in Coriolis and pressure gradient, and then you have external sources, drag and wind forcing for the momentum. And then for the tracers, you have the sources and sinks also for the I'm saying mass because I feel weird about saying conservation of volume, but it's conservation of mass, but it's incompressible, so it's conservation of volume. So we're modeling the primitive equations. So we also have hydrostatic in the vertical and Boussinesque because we have a constant density in the coefficient of the pressure gradient. And so I really like the thing I love about fluid dynamics and modeling is you can see all of these mathematical terms and you can really think through the process, and then you can test your physical understanding of the terms with idealized tests and then more realistic analysis. So the way that I think of this set of equations is that the momentum equation provides the velocity, right? And so the velocity is advecting all of your tracers around. And in the ocean, it's the temperature and salinity that's critical. The temperature and salinity gives you the density in the equation of state. You start at the surface and you integrate down, and that gives you the pressure, and then that feeds back to the pressure gradient, and it's the pressure gradient and the Coriolis force primarily together that drive the velocity, and then you're back full circle again. And then at the same time, there's all of this interaction with the other components. So you have the wind forcing from the atmosphere, the sources and sinks, the capital S here on both tracers and volume. So in particular, precip, evaporation, exchange with the sea ice. And so I have a video here to show you exactly this. This is salinity in the Arctic. We're not showing the sea ice here, but this is from a G case. So there's active ocean and sea ice in the high resolution. So this is six kilometer resolution. This is from a few years ago. So this was V1, and the dark green is fresh water. And so you can see the interaction with the other components, which is that every spring, and I'm sorry, there's a digital year on there. Shouldn't have done a digital year. Every spring you can see you have the fresh water melt, and you have a plug of fresh water from the land. There it is again. And then it mixes, and then as it goes further south into the North Atlantic, it's warmer and there's evaporation. And so, you know, the ocean by itself has all of these internal dynamics, and then it's interacting with the other components at the same time. And that's really the story of a coupled climate model. And then as you go further south, of course, it's much more saline because you have evaporation at mid latitudes. All right, so yesterday you heard that the atmosphere is on quads. We don't have quads. We're on n-sided polygons, 5 and up, typically hexagons, but it's officially an unstructured mesh, and we call it a mesh. I always think of like medieval knights mesh, because a grid kind of implies a quad. But anyway, that's a detail. And we use what's called the Trisk formulation after the authors of the paper, Thuburn, Ringler, Skamrock, Klemp, and they designed a very nice numerical scheme on a C grid, which conserves potential vorticity and is mimetic because it's trying to copy physical conservation laws. All right, so a C grid just means that your thickness, volume, and tracers are at the cell centers, and that your velocities, we only solve for prognostic velocity at the edge normal. And so then it's a finite volume scheme, but when you get down to it, it looks just like finite differences. And so there's this beautiful symmetry, which is that you compute the gradient of a vector, so a gradient at the edge, which is a vector, and it's directly between two cell centers. And then when you do the divergence, you go from the edges and you do a line integral around that and go back to the cell center. And so there's a certain beauty to the mathematics. And we create our meshes, they're called Voronoi tessellations. When you zoom in, they typically look like hexagons because they get smoothed out and the algorithms make them as regular as possible. But we can have different sided polygons. And so the meshes that you all will typically see, we have a low resolution and a high resolution mesh for V3. And I put you may be working with V1 and V2 E3SM as well. So those low resolution varied from 30 to 60 kilometers in V3, the low resolution, and this is what we're running this week, is a uniform, quasi-uniform 30 kilometers. And so I have written there just to kind of give you an idea of what that looks like. And then at high resolution, 3.7 million cells, that varies from 6 to 18 kilometers. And we vary the vertical resolution as well. We can also generate, we have tools to generate complex meshes. We can specify the grid cell size as a function of latitude and longitude and create those meshes and those tools. We use a jigsaw tool for the mesh generation, and then it's within a compass and Polaris tool, which is in this E3SM ecosystem of tools. And these are just some examples. The highest resolution we've run is global, all the way down to 125 meters, which is in this publication, just for a single layer ocean for coastal inundation. And in the vertical, it's arbitrary, Lagrangian, Eulerian. And so there's lots of different options, but everything that you'll run out of the box is Z star, which just means that everything oscillates with the sea surface height. So that's the standard option. But something to keep in mind, just even if you usually work on another component, if you're working on analysis of the ocean, keep in mind that in the atmosphere, all the layers are active. In the ocean, we end at a variable called max level cell, and everything below that is just unused in the array. And so then at low resolution is 60 layers, high resolution is 80 layers. Okay, and then there's a lot of other details of the numerical methods. We spent a lot of time on time stepping and advection and vertical mixing, and I'm not going to talk about those parts of it, but I will point out that we have documentation, and the links are here, and we've been pointing you to these links. If you always start at docs.e3sm.org and then go to Model and Components and Pass Ocean, and then we point you to other places. And the thing that you're most likely to need as a user is to have an explanation of all the configuration flags and a little bit of background on that. And we have a PDF version of that that's linked from here, but also here, that's on Zenodo, where you can find those explanations. And something that is not part of this tutorial, but I wanted to mention, is that we do a lot of verification in idealized domains. And we have a standalone, most of these components have standalone versions where you can CD down into the component directory and compile it as a standalone code for exactly this reason. So we do a great deal of verification at this level and comparing to other models with standard test cases. We probably have 100 test cases that can auto-generate in these Compass and Polaris tools. So the developers spend a lot of time on that. What you see in E3SM is a global ocean model with all the realistic bathymetries and boundaries, but this is where we spend time doing verification.
So thanks, Mark, for this description of sort of the detailed numerics and discretization of that we rely on for the ocean modeling. This next section, I want to talk about kind of more the practicalities and challenges of ocean modeling. And in particular, what I want to highlight here is the challenge of having a variety of spatial scales in fluid dynamics. And so in the center here, this is the grid cell that Mark just presented, the details of en-pass ocean, where we have processes like advection, transfer from one cell to another horizontally or vertically. And typically, this is a horizontal scale in our global meshes of maybe 5 kilometers to 100 kilometers. Vertical scales between our different layers of maybe 5 to 500 meters. And we're talking about processes that we're going to represent in the time scale of maybe minutes or hours. And then we use those, we combine a lot of these cells, as Mark presented, up to millions of cells to try to represent the entire global ocean. And the global ocean has the spatial scales of thousands of kilometers for ocean basins. And depth, we're talking about, maybe 500 meters to 4 or 5 kilometers for the full depth ocean. And here in the context of climate modeling, we're interested, in the maybe shorter seasonal timescales, but for climate really up to 100 years, or if we're trying to do model spin up, we might need to run thousands of years of simulation. And so that's a big range of scales from this numerical grid to the large scale coupled and ocean dynamics. But what I want to highlight is that technically we have much smaller scales in the real world. The water that you have in your coffee cup or in your glass is the same water as there is in the ocean. And so in terms of physics and fluid dynamics, we know that there are processes that happen at much finer scales. If you're putting sugar in your coffee this morning, because I thought salt in your coffee wouldn't be a good image, and you're mixing it with your spoon, things are happening there in terms of diffusion and mixing on the scales of millimeters and on the time scales of seconds to minutes. And so part of the challenge is that in our ocean model for climate, we really have this range of scales from the grid cell and higher up to the global ocean where we can resolve things. But there is really not a good way to realistically represent those finer scales of your coffee cup, because that just would be too expensive to bridge from the really small scales to the large global scales. And so part of the challenge is that for those smaller scale processes, we're looking for simplified representations of those small scale processes that we might include at the grid cell or a couple of grid cell levels. And so when we're talking about parameterizations, Mark has mentioned parameterizations a few times already, we're talking about a simplified representation of a missing process or physics that would be too costly to include explicitly in the model. And there are many processes happening at the fine scales, and we can decide Are those ones that we think are important enough to include in parameterizations? Are they those that we can neglect? What are the key effects that we do want to include? And so if you talk to an ocean modeler or someone who does oceanography at the finest scales, you might hear lots of terms. Things, mixed layer eddies, we choose to represent upper ocean turbulent mixing. Any boundary layers, like the literal, like viscous or turbulent boundary layers, they're really small scales, internal wave breaking, Langmuir turbulence. These are all processes that I would contain in the coffee cup. And the question is to say, as a modeler, do we choose to represent them? Do we have a good simplified representation where we might be able to include their effect at the grid scale? And so if you are an experienced modeler in other components or other frameworks, I'm sure this sounds familiar. This is a sort of decision that as modelers, we have to make. What is it that we include in our model? What is it that we neglect? What is it that we simplify in a way to afford the simulations that we need to run? I'm going to talk a little bit more in detail about parameterization of mesoscales. And what I wanted to highlight here is that mesoscale dynamics are dynamics about maybe order 1 kilometer to 100 kilometer. So they're exactly in the range of resolutions that we're able to represent. So if you think about the E3SM configurations, our high resolution might be, the finest resolution might be 6 kilometers. Our coarse resolution might be 30 kilometers. We're exactly in what we call kind of this gray area where the high resolution might be able to resolve the mesoscale dynamics and the coarse resolution needs it parameterized. And so I'm going to give examples of 2 of those parameterizations, mostly because if you talk to ocean modelers, they will mention it. But the key is that those 2 are going to be turned on or off depending on the configuration that you're running. So that's something to think about in your whichever simulation you're looking at. What is the resolution? What are the processes that we're representing? Because that has important consequences for which options to turn on or off in your model. So this is one of them, the Gent-McWilliams parameterization. People call it GM. So this slide is mostly to give maybe non-oceanographers a sense of what that is. What I want to highlight is that in the red box here is the actual flag. And so if you're running coupled simulations, one thing you might want to check, you'll look at nameless files later today, but you might want to at least read, is this turned on, is this turned off? So this is the kind of flag that you're looking for. And here again, we're looking at the effect of smaller scales, eddies, that tend to, so this is your density surfaces in the vertical, that's a vertical section of density surfaces. And what happens is that when you have very sharp gradients like this, you're going to develop an instability. That's little wiggles that appear here. And at high resolution, you're able to represent those wiggles, but at coarse resolution, we're looking again for a simplified way of representing the effects of those mesoscale eddies. And so we think about those mesoscale eddies as flattening, so changing the slope of those isopycnals by doing transport of thickness. So we're using this U star as a large scale representation of those smaller scale tracer interactions. So GM is used to reproduce the advective transport by unresolved mesoscale eddies. Again, what's important to remember that it depends on resolutions and the scales that you're able to resolve in your ocean model. So it might be turned on or off, or as we're going to talk about, it might be turned on or off in different parts of the same configuration of the same simulation. There are different flavors. Simplest ones have sort of a constant coefficient. Then you can have ones that vary in space in the vertical and the horizontal. But what's kind of important for you to remember is that we're adding this velocity, the U star bolus velocity, that is going to be dependent on the slope of the density surfaces and some coefficient kappa that we're able to parameterize and choose. A similar flavor, second ocean parameterization for mesoscale dynamics, we call it ready. And here is to represent a different part of the effects of those mesoscale eddies. Again, if this is your density surfaces and has a strong slope, if you remember back to Mark's part about the equation of state, what's important is on the ocean, the density is driven by the combination of temperature and salinity. So you can have a situation where you have lines of constant density, but you have changes along that constant density. You can have changes in temperature, or you can have changes, for example, in biogeochemistry if you have a particular tracer in your model. So what you have is, you have this gradient, and the small scale features lead to some mixing along this line of constant density, which we parameterize as a diffusion of that gradient. So you start with a gradient, but you're able to diffuse, erode this gradient. And so we parameterize that with an additional flux. Again, this flux is dependent on the slope of your density surfaces, and you have some control over the magnitude of that with a coefficient kappa. There are different flavors that exist. Again, this is one of them that is dependent on resolution and scales. And so if we're looking at a particular configuration, they might be turned on, turned off, or have a factor to reduce their intensity in different regions. I think I have time for this little quiz. Wake up time, this is quiz time. So this here is a plot that shows the resolution, the grid resolution in degrees that is required to resolve mesoscale dynamics. So if we think about mesoscale dynamics, unresolved is your coffee cup. Resolved is actually your grid scale and higher. The different colors on the plot show which resolution would you need for your mesoscale dynamics to fall into your resolved part, where you can maybe turn your parameterization off. So my question for you is, okay, if we use a very low resolution E3SM configuration, let's say QU240, which is a way to say quasi-uniform 240 kilometers. Your cells are about 240 kilometers. So now is the quiz. Your mesoscale dynamics, are they your coffee cup or are they your grid? Resolved or unresolved, and where? Unresolved. Okay, so if you look at the plot for 240, we're in the gray area, literally, meaning we're coarser than 1 degree resolution. And so coarser than 1 degree resolution, where is the mesoscale dynamics resolved? The answer is basically nowhere. Maybe a little bit in equatorial dynamics, but not really. And so here you have your coffee cup everywhere. We need to parameterize it everywhere. What happens if you have a 30 kilometer resolution? Your standard sort of low resolution mesh in E3SM is ICOS 30, icosahedral 30 kilometer. What happens at 30 kilometers? Any guesses? 30 kilometers, you might be
1/3 degrees.
Yeah, about 1/3 degree blue. So where is the mesoscale dynamics resolved anywhere? Yeah, equatorial tropical area we might be resolving. What are the areas that are not resolved? Everywhere else. Yes, absolutely. So what happens at high resolution if we have, let's say, 5 kilometer? That might be, you know, depending on your latitude, that might be 1/12 of a degree or finer. your yellow area. So again, here your mesoscale dynamics are going to be resolved in most of the sort of tropical mid-latitude. But you still have areas such as the very high latitudes that you see highlighted in red and yellow, where your mesoscale dynamics are not necessarily resolved. And in coastal areas, you will notice that the coastal areas are red. This is because in shallower oceans, you need higher horizontal resolution to be able to resolve the mesoscale dynamics. So this is just to give you a sense that in your configurations, depending on the relationship between the horizontal spacing, the grid resolution, and the local dynamics that are dependent on latitude and depth, parameterization might be turned off, parameterization might be turned on or off. And we typically have a Tabor where we have a factor that multiplies this parameterization so that it can transition from areas where we're not adding any parameterized mesoscale dynamics to areas where we are adding parameterized dynamics. Thank you all for listening. So, this was your little exercise. There are many more ocean parameterizations that you might hear about. Convection, KPP, which is your upper ocean mixing, mixed layer eddies, which is your V3. It's a new feature in V3, different viscosities. Some of you who might be particularly interested in the ocean component, you might have opportunities this week to play with those parameters. Overall, the main point is these parameterizations tend to be turned on everywhere in most, in the simulations you'll run. And you might need to adjust or double check values for parameters depending on the resolution, but usually they'll be all turned on. So that's easier than the two that I just mentioned. So in practice, how do we assess ocean models? We know that there are common sources of errors in ocean modeling. You can have inaccuracies in the forcing field. You can have incorrect parameterizations or missing physics, either because we don't know how to represent them or because including them would be very costly. We can have errors that come from the numerical scheme precision. Again, some of the details of the advection scheme, for example, there's a choice between how precise do we want our advection scheme versus how fast do we want to be able to run the model. And then there are always truncation errors, meaning for the machines we're always truncating, we can't store with infinite accuracy or precision. And so you have truncation errors that will propagate through the climate system in a chaotic, given that the climate system is chaotic. Briefly, I want to show you that part of the ocean validation is observing the real ocean and then assessing how our model is doing compared to observations. A couple of things I want to highlight is that if you go back to the 1980s, these are tide gauges that have at least 1 year of data. So if you're looking to assess climate or sea level ocean state back in the 1880s, you have very little information. Similarly, one of the things we measure most frequently is the temperature in the ocean. On the left is a 1950s plot of ship-based measurements of temperature. And you can see that you have very much fewer, I guess, temperature profile measurements, and they're all kind of focused on the Northern Hemisphere. In the 2000s, we have way more temperature profiles. Since then, we've also added measurement from altimetry. You can measure temperature from satellite. You can also measure, as I said, altimetry, which gives you an estimate for the ocean currents. And here, the satellites have really improved the spatial coverage of observations. But partly, one of the downside of satellites is, as Mark mentioned, the ocean is opaque. So we get a lot of surface information, but very little information at depth. We've also added Argo floats, which were those yellow instruments, which gets thrown overboard. And you can see on the 7th of May, we had a little under 4,000 floats drifting around the ocean, making measurements. And these go up and down and are able to measure the properties such as temperature and salinity in the water column. We also have new floats that are able to measure things like biogeochemistry, but those are rarer. And so all these observations are summarized in often gridded data sets, such as the World Ocean Atlas, that we can use for comparison. There are other things you can use for comparisons, including other model simulations or reanalysis products. The things I want to you to keep in mind is that when you're comparing ocean models to data or some other benchmark, I want you to look for, okay, what is the data source and what is the period that you're looking at? Again, as illustrated in the previous plots, if you're looking at, mimicking the 1950s, we have a lot less information than, mimicking the 2000s or 2010s. Different regions have different sampling. North Atlantic, historically much more sampled than, say, the Antarctic shelf. And different variables have different sampling. So we have a lot more measurements for temperature and salinity, especially in the upper part of the ocean, than we do for things like deep ocean or things like velocities. We have very few direct measurements of velocities. And the last point here, internal variability, is to say, be it for an ocean model or a climate model, this is a chaotic system, so a small change can propagate through the system and give you a slightly different scenario of what this particular year is like. Is it a wet year? Is it a dry year? And so when you're comparing a historical data set with a coupled climate model, you have to remember that the timing of events don't necessarily match. What matters is matching the statistics of events. And so as part of the impasse analysis practicum later today, you'll have an opportunity to look at comparisons of ocean data with observational data sets. And so in the practicum later today, but also later as you analyze a couple of climate simulations, I want you to remember, okay, when you look at plots, remember to assess what is the correspondence between your ocean model data and what is and the observational data sets. And do you expect it to be a very close alignment, or are you looking for the statistics of those two to agree? Okay, last quiz. Going back to the big picture, we're considering the ocean model within E3SM. And that means that the ocean model is exchanging fluxes with other components and other parts of the climate system. What sort of fluxes can you think of that the ocean needs or sends back to other components?
River fluxes.
River fluxes, that's a very good one. Usually released near the coastal boundaries. Any other connections?
Smell.
Ice melt, yeah, so you can have an exchange of fresh water, salt, also heat, interacting with either sea ice or land ice. Exchanged with what?
Salinity would be with the ice.
Yeah, salinity with sea ice, yeah.
Everything.
Temperature with everything, okay.
The atmosphere, maybe with the ice.
Absolutely, those are good, those are
Nutrients.
all good. This is not an exhaustive list, it's just giving you a sense. We have river runoff, we have interactions between the ocean and the atmosphere, things like precipitation, evaporation, heat fluxes that are associated with that, wind stress, where you have a momentum exchange, ocean sea ice interactions, where we exchange heat, water, and salt with the sea ice component. And beyond that, nutrients, carbon fluxes, and we also have freshwater fluxes exchanged with land ice, which are not currently, which are currently implemented in some configurations of E3SM. On that note, since we're talking about ocean sea ice connections, we'll have a short break in a second. Okay, the coupled fluxes are influenced by various decisions, such as your coupling frequencies, maybe smoothing of different terms like the runoff, or the formulation of those fluxes. Again, these are things just big picture for you to keep in mind that there are some decisions that are encapsulated in how we calculate those coupled fluxes. So we're going to take a short break, take some questions right now on the ocean, and after this, we will switch to the sea ice presented by Darin. Yes.
How is the initial state of the ocean? Pained. How long does it take to spin out the liquid into the ocean?
Okay, you mean kind of the classic configurations of the
Yeah.
coupled model? Do you want to sort of?
Sure, we start with the climatology. What's the data set?
PhD.
PHC, anyway, polar hydrographic climatology. And then the velocity fields spin up quite quickly. So just to get the time step and everything within a few months. But then we usually run for, we like to run for decades in order to have a stable climate and allow the tracer and salinity to adjust internally to the model dynamics. But in order to run historical simulations, we run for thousands of years at repeated 1850-year control runs.
How long are you finding it takes the control run to stabilize?
Depends on what you mean.
Exactly.
It kind of
Depends on what you mean by stabilize. Which variable do you care about stabilizing? Some of them, especially in the deep ocean, can still be drifting. But yeah, we usually run it, up to hundreds, thousands of years to have a
Right.
stable.
And that's an issue at high resolution because you just can't afford it. And so it's a kind of at high resolution, it's a 50-year minimum really to get everything stabilized and not drifting too much.
I didn't notice you didn't have anything about tides. Do you not consider the influence of tides within, climatological timescale?
So we do have tides in for the ICOM project. And we have a couple papers out on it, and we looked at the effects of changing climate on tides. But for global ocean models, for the typical things that we are interested in for climate change simulations, we don't need tides or haven't used tides. But that's something that we are not in the mainline E3SM project, but in the ICON project, we're looking at that and we've spent some time on it. So it is actually in the model.
Yeah, so there is an option to have barotropic tides in the model. It's not in any of the standard configurations. So unless this is a very specific project that requires that, you might not.
Okay, I was just curious if the mixing due to barotropic to baroclinic conversion, is that just not a big enough impact on long timescales to really, or is it just computationally expensive to do?
Yeah, I think it's not, so baroclinic tide's not fully implemented yet, and also it's quite expensive to run. And so, yeah, there is none of the long-term climate simulations that we have the tides in.
So the mesh that I showed that went down to very high resolution on the East Coast, that was for the purpose of these tidal simulations. And really, once you start doing coastal inundation and you're asking what's the risk of inundating to this far inland, you have to have tides included in those simulations.
Wondering a little bit more about capturing these subgrid scale processes, and I'm wondering sort of like, are there any reduced order model developments or other modern multi-scale approaches that are being used to try to capture these processes?
There's a lot. I mean, so these variable resolution models themselves is one way to deal with multi-scale.
Yeah.
In that, we're developing meshes where we can resolve in the area of interest. And there's the classic methods are GM and ready, which is what you for mesoscale, which is always what you hear. And then there are, in the last 10 or 20 years, there's new ones coming out. And you can always look at the publication. So this is why we've added the submesoscale parameterization just in the last version. So the answer is yes, there's a lot of smart people out there thinking about these things. And as developers, we try and, talk with our fellow ocean modelers, and you always have to prioritize what you spend time putting in the model.
Yeah, and I think an effort to develop new parameterization like is a field in itself.
Sure.
And so what people usually do is that they might run sort of LES or like finer scales models and then try to take from those failed experiments some statistical, simplified function. Part of the challenge is that often, this is really hard to pick one function that might be consistent across different forcings or across different scales. And so there are specific efforts, like, I don't know if you're familiar with the idea of climate process teams. Those are particular funding efforts that look at bridging between sort of the idealized process studies and the climate models and the climate scales. And part of the difficulty there is that if someone has a very, very good but very fancy detailed parameterizations, it might not be stable enough to run in a climate model. It might depend on certain scales or certain details that are not ready in the climate models. And so being able to bridge that is really just challenging in terms of collaborations. But there are definitely funding efforts and specific work on that front. And sometimes, with machine learning enhanced parameterization, with the idea of can we learn a pattern with machine learning that we would be able to feed back into the model. So definitely an effort. If you're passionate about this, we totally need continued work on those to bridge those scales.
Are we in the stage to combine the wave watch and the ocean modeling, or we still have to wait for a few more years?
So it depends. No, yes, we are at the stage. Wave watch can be run with the ocean E3SM framework. At the moment, there's still a coupling happening. So there's coupling with students. The coupling with the atmosphere is currently under development. People are working hard on that. Part of the issue is that wave watch is very expensive. So you can have it in the framework and run with it. But the question of saying wave watch is a wave model for those who are there. The question of saying, can you afford to run it in a fully coupled model? And we might be able to do shorter term simulations, but at the moment, it's not viable to run, hundreds of years of climate simulations with WaveWatch 3 active in it. Does that answer your question? Okay.
I had a couple of questions regarding viscosity.
Yeah.
So one is that, so do you keep the hyperviscosity same throughout the mesh or throughout the computational domain?
No, it varies. So the del 2 coefficient varies just with the grid cell size, and del 4 coefficient varies with the cube. And so it just computes it on a per grid cell basis.
So yeah, there's a factor in.
There's a standard
to
scaling
scale
for
it
that.
depending on the resolution.
The other is, so when the salinity and temperature gradients are very sharp,
Yes.
so that might, like viscosity is dependent on those two things, I assume. So do you consider like the stratification in viscosity ever in any of your studies?
So the horizontal viscosity does not depend on temperature and salinity, but the vertical mixing, you saw KPP in there a few times. There's various vertical mixing parameterizations that do depend on the stratification, and those are quite in-depth parameterizations because you just don't have the vertical resolution to resolve things. So again, it's a subgrid scale parameterization that's based on observations.
So you mentioned that there are inactive layers. I wonder what are the criteria to decide if the layer is inactive, and does that dependent on resolution?
So the really simple answer is that we use a Z level system and we have observational data sets of bathymetry. And so it's simply that when the layers are below the bathymetry, they're inactive below the bottom. Now, there are more complicated vertical layers that we can use. So we've tested with sigma and hybrid, sigma, Z, and so forth. But we've used just the standard Z star with the inactive layers below the bathymetry for the standard sorts of simulations that you'll see.
Does that answer your question? Okay, so mostly, yeah, the geometry of the ocean basin means that even if numerically we have some cells there, we turn them off. If there is no water in that cell.
You mentioned the nuclear ID is new in E3SM version 3. So I just want, we have the high resolution version 2. It can also resolve the ID process within the mixed layer. I just want to know what's the difference between this layer ID with some other mesoscale ID and the sub-mesoscale ID.
Okay, well, the mixed layer eddy is a more of a submesoscale impact. So it leads to restratification of the upper ocean, so reduced mixed layer depth. And so this is finer scales than those mesoscale dynamics that I talked about. And so it wasn't included in version 2, although it was included in version 2.1. So it's just adds a little bit of transport in the upper ocean. It's mostly a very located in the upper part of the ocean to restratify and impact the mixed layer variability.
So I think we should move on to Darin.
We should.
Sure.
All right, next we'll have Darin talking about the sea ice model.
Good morning, everyone. My name is Darin. I'm at Lanel on the working on the sea ice and polar teams. And so here I'm going to be talking about the sea ice component for E3SM. So first off, what is sea ice? It is frozen ocean water, distinct from land ice that is formed from snowfall that falls on land and then becomes compacted into ice. Sea ice is frozen ocean water. It's typically very thin, but can have an extensive quite an extensive horizontal extent. And it has a bit of an outsized importance in the climate system due to the fact that it drastically alters the albedo. So at any given time, sea ice covers about 4% of the Earth's surface, but it can change the albedo from a dark ocean, which will be absorbing much more energy, to a very bright reflective surface. Sea ice also insulates the atmosphere from the ocean, which can drastically put a barrier between heat and moisture exchange between the two components. And so what do we need in a sea ice model for climate applications? We need a reasonable mean state and variability. So this is looking at sea ice concentration, thickness, and conservation of mass and energy budgets. We need realistic ice-ocean atmosphere exchanges of this mass and energy. And we need the response of sea ice to climate perturbations to be somewhat realistic because sea ice is key to some climate feedbacks. The thickness of sea ice is very sensitive to thickness, particularly when we get to very thin layers of sea ice, which can melt very quickly, resulting in an exposed ocean surface that then has a drastically decreased albedo. So on the right here, showing an image of how complex this sea ice landscape can be between open ocean areas on the left here. On the right, we have melt ponds on the ice surface. So this is meltwater that is melting, melting on the sea ice surface, along with some ridged features that are the result of mechanical distribution from sea ice flows flowing into each other. So this can get a bit tricky for sea ice modelers because sea ice is a pretty passive-aggressive component in the climate system. It's passive in the sense that it's really responding to the climate conditions around it. If the air temperature in the Southern Ocean is a couple degrees biased too warm, sea ice won't form. If the ocean surface in the Labrador Sea is too fresh, sea ice will form where it shouldn't. And so the result of these, small biases and other components can be the difference of sea ice being there or not, which can be the difference between the albedo being 90% or 30%. Be the difference between there being a barrier between the atmosphere and ocean that could exacerbate existing biases. So over the years, sea ice models have gotten considerably more complex. So this is a schematic that was created for the ice pack model, which is really a column physics model that comprises of all of the processes that take place within a single grid cell column. So just for some historical context, back about 10 years ago when E3SM was first being formed and MPAS sea ice was starting to be developed to be the sea ice component for E3SM due to its, which was really, so that the sea ice model was built on the same framework, the same MPAS framework as the ocean model that allowed for regional refinement in an unstructured grid. All of the column physics that had been developed over the previous 20 years or so in the former sea ice model SICE was peeled out and pulled into its own software package that could be then used for various sea ice models across the globe. So there are a number of thermodynamic processes that take place within IcePack, as well as interactions with various forcing terms from other components, along with ridging or mechanical redistribution. So essentially everything that's not dynamics and transport is handled through IcePack. And to go from picture to sort of words of what the various terms are. So IcePack has, divided into a few different categories. There's morphology that handles the thickness distribution, snow distribution, melt pond, and brine and enthalpy distribution. Features that are being developed now is capability for a flow size distribution, which is a statistical representation of what various flow size there are within a given grid cell. And then for V4, a so-called ridged ice distribution, which is really macro porosity in sea ice, which I have a picture for later that nicely demonstrates that. There's a standard physics of interaction of heat and mass between the other components. And then there's also biogeochemistry. So what does MPAS sea ice do at a high level? There's dynamics, calculation of a momentum equation, a stress tensor, and then transport. And then there's mechanical redistribution. There's thermodynamics, which is represented by a so-called mushy layer. There are various melt terms and growth terms. And these are all integrated together in what is the ice thickness distribution. So I'll talk a bit about on the next slide. MPAS sea ice is a continuum model, so we don't model individual flows. There's really a concentration of sea ice within any grid cell, and that concentration of grid size of ice within a grid cell can take various thicknesses. There's other physics that I'm not going to be talking too much in detail about, such as melt ponds, advanced snow physics, biogeochemistry, flow size distribution. That's all handled within IcePack. And then what MPAS sea ice itself does, has various analysis members, handles the driver coupling interface with the other components, as well as IO. Yeah, so MPass sea ice shares the same grid that as MPass ocean. Instead of, but a difference is that MPass sea ice uses a so-called B grid formulation, where the sea ice velocity, both components of sea ice velocity are defined on cell vertices rather than normal edges. And sea ice concentration and volume are defined at the cell centers. And as I said, MPass sea ice is a continuum model. Individual flows are not resolved. The main equation for sea ice dynamics is the momentum equation, Newton's second law, F equals ma. This is the actual equation. So we have mass times acceleration. There's internal stress term, wind stress, ocean stress, Coriolis, and sea surface tilt. What we actually solve is just a slight change where the total derivative du dt, we only solve the partial derivative with respect to t. We neglect the invective terms, which sort of makes sense in a continuum model. What I want to say here is that the bulk of the work is really in this solving of the internal stress term, and solving of the stress tensor. And included in that is are any assumptions about the rheology of sea ice. And that's very important for determining the material properties, such as the strength that will later have impacts on convergence or divergence of the sea ice pack. So a bulk of the dynamics physics is in this so-called elastic viscous plastic EVP rheology that is commonly used. Now, once the momentum equation is solved and we have the velocities defined on the cell vertices, we then need to transport quantities. And so this is done by incremental remapping, which is designed to be conservative. So this C term here, think of that as the concentration of sea ice within a particular grid cell. So determine the flux of sea ice concentration across a cell edge. We use the velocities to form backward trajectories to find departure points, which are these Ds. Calculate the area of this quadrilateral and sea ice concentration in that shaded region, and that is the flux across the cell edge. Now, this is a bit expensive to do once for one velocity field, but once we do it once, then any additional tracers that we have are very cheap because it's all using the same calculated quantities from the same velocity field. So it's conservative, monotonic, it does not introduce new extrema, and scales well with additional tracers. Sea ice thermodynamics, the radiation budget is essentially a heat budget for the sea ice. So there's net long wave and short wave heat fluxes at the surface. And some amount of short wave radiation is allowed to penetrate through various layers of the sea ice. So what's shown here is sort of various layers of a sea ice with a snow, with various snow layers on top of that. So there could be in any particular grid cell, areas of open ocean, bare ice, ice with snow at various thickness categories. Each of those requires its own radiation calculation. So in the thermodynamics part of the MPass sea ice solve, it's really the radiation that is the dominant computational cost. Sea ice thermodynamics is based on a so-called mushy layer, which is really that sea ice is a multi-phase, multi-component material. Multi-phase, it's a mixture of solid and liquid. Multi-component, a mixture of salt and water. So there can be brine channels within the sea ice pack. So I guess the total solve of heat and mass throughout a particular column is really a calculation of heat fluxes at the surface and the bottom, along with a Darcy flow of essentially salt and water throughout the mushy layers. So we've talked about, I guess, dynamics and thermodynamics, and this is all really integrated together in what is the ice thickness distribution. So the thickness distribution is influenced by each of these processes, top and bottom melt, bottom accretion, which is congelation, frazzle formation, which is ice crystals formed in the ocean at supercooled temperatures, and snow ice formation, which is really when snow falls on the surface of sea ice that then falls below or can come in contact with ocean water and then freeze. Along with mechanical redistribution, which is ridging of sea ice when flows collide together and form these ridges. So the sea ice thickness distribution is really another conservation equation. So the thickness distribution G here is conserved across the sum of these processes, across velocity in and out of a grid cell, mechanical redistribution, and the rate of thermodynamic growth. So I mentioned this earlier, but we typically in MPAS sea ice run with 5 thickness categories, and this is an idealized version of what this PDF of ice thickness distribution may look like. Practically, we have more of these 5 thickness layer or thickness categories. Most of the concentration is in the thinner ice categories. So thermodynamically, as ice is growing, in this case, the ice thickness distribution will shift from open water or thinner ice categories over to thicker ice categories. And similarly with mechanical redistribution, that can also shift the weight of the distribution from open water or thin categories to thicker categories. Here's an example of an actual sea ice thickness distribution. I got this from Andrew Roberts, who's standing in the center right there. So these were measurements they took up in the Beaufort Sea over a couple of different days. So this is observationally actually what it looks like. Earlier when I mentioned this ridged ice distribution or macroporosity, that's a development coming into MPAS sea ice later down the line. This is the sort of example I had in mind, where we have you standing in front of these massive ridged structure where there's huge areas of open air within the ice pack there. It's not all solid ice. So that's what's meant by macroporosity, which is currently not captured in the model. And so last I wanted to finish up what this actually looks like. So this is from the high resolution campaign from V1. So showing an annual cycle of sea ice thickness. Now the ice is actually a bit thicker here than we'd like. I'll show some preliminary results from our V3 simulation campaign later in the week, where we've, after a couple of bug fixes and improvements to the model, have really gotten a much more realistic ice simulations. And on the right here is just sort of a zoom in of the actual mesh around a case spot or in East Antarctica. Just to, again, show this is looking at about 6 kilometer resolution here. Mark and others have pointed out the documentation. I'd highly recommend for further information, looking at that, because we put a lot of work into getting that together. Along with the MPAS sea ice overview manuscript, really has references and more information on sort of each of these aspects that I've talked about. So that was it. Any questions? Yeah.
Does MPAS, like is land fast ice, so like the raw and ice shelf, is that included in MPAS sea ice? Is that more in the land ice?
So that would be in ice pack. So that developments are in, or some groups have put that in ice pack, but it has not made its way into sport into MPAS CS yet, but it is to be planned. Yeah.
You missed this, but slide 18. So that's the PDF or a histogram of sea ice and observations. What does the histogram look like in the models? Is it actually a bin histogram? Is it?
Yeah, I don't have it really looks like a decaying exponential, essentially. I mean, so most of the concentration or most of the weight is given to smaller categories, but
How is it? How is the PDF parameterized in the model?
That's a good question. If the size, if the thickness category boundaries are fixed or allowed to evolve, and I honestly don't know the answer to that.
How many there are?
There's 5, typically 5. I mean, you can, it's a nameless option, so you can set as many as you want, but 5 is what we typically run with. Yeah.
The ridge and keel formation, is that included in any fusion functions now?
That's going to be in macro porosity. That's a development. Yeah.
Gotcha. And would that then influence potentially the atmospheric and ocean forcings, things like that? How is that done now? Is it just a drag function or something like that?
Yes. So I mean, there's an ocean drag coefficient that is a tunable parameter. But yeah, that's about the extent of the interaction with the other components now.
And then one other question. And then in terms of the rheology, it's probably EVP? Are there any research efforts looking at different rheologies, how it performs? You know, the great thing about MPAS is that we can do variable resolution, but how well does that rheology perform under high resolution?
Right. Not that I'm not aware of such research activities, but certainly at higher resolution, we're bumping up against the limit of what a continuum model is reasonable for. But I mean, there are a number of nameless options affecting the rheology. In addition to EVP, there's also EAP implemented in the elastic anisotropic plastics. So yeah, there are options in there, but I'm not aware of research efforts into that. Yeah.
The MPAS as a brine rejection scheme explicitly.
That's part of the mushy layer. So let's see. I included like the main equations here, but there are additional equations for brine quantities that are not included here. So I'd reference, this Adrian's paper from 2013 is the original mushy layer parameterization that would have it.
So the extra salt goes into the ocean. The change in density and then change the.
Anything that's flushed out through the bottom layer.
Questions? Well, if not, let's thank Mark, Alice, and Darin again for. Everyone can hear me? All right. Thank you, everyone, for coming back on time after the break. Now we have 3 exciting talks talking about the land modeling. And so Dan Ricciuto from Oak Ridge will start us off with land modeling. Then we'll have Tian Zhou from PNNL talking about the river modeling, and Jennifer Holm from LBNL, Lawrence Berkeley, locally, will be talking about the PACE modeling. So start us off.
All right, good morning, everyone. Hope everyone can hear me all right. So I'm going to give an overview of the E3SM land model, or commonly referred to as ELM. So I'm just going to start with kind of what's the purpose of a land surface model like ELM. So a few decades ago, when the field was just kind of getting started out, they needed a bottom boundary condition for the atmosphere, something to provide radiative and energy fluxes. And those the land surface models have expanded kind of greatly over the last few decades and now can predict things like ecological carbon nutrient fluxes in addition to the energy and water fluxes and pools. They've begun to integrate more sophisticated biogeochemistry here on the right side, which I'll talk a little bit more about carbon, nitrogen, phosphorus. But essentially, we're predicting water, energy, carbon, and nutrient fluxes and feeding those into the atmosphere. And so the basic structure of ELM is quite a bit different from the atmosphere and ocean models that we've heard about. They typically focus on just 1D interactions. And so each grid cell has a structure first to represent subgrid variability, kind of small here on the bottom right, but I will go into each kind of layer or level of subgrid variability. There are several of those. Energy, water, and carbon flows are tracked across layers and vertical columns. And so you can see here in the center, the columns, there's a soil, 10 soil layers that kind of exponentially increase in depth, such that the top 5 layers are about 30-ish centimeters, and you get down to the 10th layer, it's about 3.8 meters. And then there are 5 additional layers to represent bedrock that go down into the tens of meters. And so in the land model, there's not really a single governing equation, right? There's many, many different interacting processes that are represented. And so, for example, photosynthesis, the flows of carbon through vegetation and soil, soil energy and hydrology. And in the default version of ELM, we do not have horizontal interaction. So there's no communication between grid cells. So that makes it pretty easy to parallelize. It makes it easy to run sort of single grid cell, which we often call site simulations, and kind of regional simulations if we just want to extract, say, a continent and run that. And so on the right side, and we typically run it, as we're running ELM within coupled simulations, running on regular grids from 100 kilometers down to kind of more recently, much more refined or up to 1 kilometer grid sizes. It can also be run with a kind of an unstructured grid, given that there's no horizontal communications. It's relatively easy to set up. And so here's a little bit more detail on the nested hierarchical subgrid structure. And so at the top level, we have grid cell, which I mentioned. Then we have the next layer, topographic units, so we can represent variation in elevation, slope, and aspect within grid cells. We can have multiple layers or multiple levels of topographic units. Under that, we have land units. And so we have things like, say, natural vegetation is one type of land unit. There are also other types of land units, including urban and wetland systems. Below that, we have columns, and so those kind of soil columns that I just showed in the last slide, and so that can represent multiple layers of soil and snowpack. And then on top of columns, we can have multiple plant functional types, and so different types of vegetation, different vegetation communities, or also bare ground. And then under that, we can have continuous variation in the canopy and plant canopy, and resolve sunlit and shaded leaves. And so a little bit more about each of these. Again, grid cells, they can be rectangular, they can be unstructured, they can be regionally refined, and there's a lot of work going on now. Given the low relative computational expense of the land model compared to the other components like atmosphere and ocean, we think there's opportunity to really go for some higher resolution simulations up to 1 kilometer. So a little bit more about topographic units. And so subgrid macro topographic variation is represented with discrete classes of elevation, slope, and aspect. And here's a map of kind of the number of topographic units in each grid cell. And of course, you can see in more topographically complex areas, mountain ranges, we tend to have more. topographic units up to 12 per grid cell, and then over flatter areas, it can be represented with 1, where there's really not a whole lot of topographic variation. So part of the reason for this is that it can be used for surface weather downscaling, and so we can have atmospheric inputs that are downscaled to represent differences in elevation, so cooler, more humid or wet conditions and higher elevations, for example, and upscaling of land fluxes back to the atmosphere. We're also exploring using this capability for microtopography. So for example, in wetland systems where we have hummock hollow type systems, those are quite important in directing hydrologic flows and important for the fluxes of carbon and methane, for example. At the next level, we have land units. And so again, each topographic unit can have 1 or more of these land units, and they're geomorphologically distinct. And so we can have natural vegetation, for example, and I think that's probably the largest in terms of overall land area represented by specific types of land units. But there's also cropland, which is another big component. Pasture, wetland, glacier, urban is another component, and lakes, for example. So then drilling down into the column scale, and so each land unit can have 1 or more columns. The natural vegetation, for example, would have a single column where all the plant functional types exist within a single soil column. The urban land unit, I believe, has 3 columns. And so these columns represent vertical layers in the soil that I described before. And so structural, thermal, hydrologic, and biogeochemical quantities, and also the potential for multiple snow layers where there's snow to be predicted. And so again, the default model does not represent subgrid flows, but we are exploring in several different versions, kind of research versions of the model, implementing kind of these subgrid flows between columns, and also coupling in some cases with complex reaction networks. So a little bit more about some of the soil biogeochemistry that's represented in ELM. So it's relatively simple. It's a first order decomposition model. And so that means the decomposition rates are proportional to pool sizes. And here I'm talking primarily about carbon and nutrients. And so for each of these pools, we have a rate constant that can be modified by temperature and moisture here, kind of on the upper right. So again, all of these contain carbon, nitrogen, and phosphorus. And then what's going on is we have nutrient mineralization or immobilization within the column is based on stoichiometry. So for example, the ratio of carbon to nutrients in these source and destination pools. And then there's also competition for these nutrients. And so the vegetation has a certain amount of nutrient demand from the soil that's required to grow in terms of leaf area, for example, or biomass. Soil microbes are also demanding nutrients in order to decompose the materials that are in the soil. And so what's used in the default version of the model is called a relative demand approach. And so based on the amount of demand between the plants and the microbes, if not enough is available to satisfy that total demand, it's just allocated relative to those individual components. In this example, or in the default version, we're using a converging trophic cascade. And so what's happening is as vegetation dies, it becomes litter. So there's 3 different types of litter that can be represented with that vegetation death or input into the soil. And each of those litter types decompose into soil organic matter 1, 2, 3, and 4, depending on its composition. And so as that number increases 1, 2, 3, and 4, it's longer and longer lived in the soil. So when you get to soil layer organic matter pool 4, it's relatively long lived in the soil. And also these decomposition rates decrease with depth. So it lasts, kind of lasts longer as you go down in soil depth. There are alternative frameworks for both nutrient competition and a reaction network, which I've linked there if you wanted to see more details about how they're implemented. And so now a little bit more about plant functional types. And so each column can include one or many plant functional types that can have continuous variation in the plant community composition. And that is generally prescribed by remote sensing inputs, or in the case of needing to go out into the future, future scenarios. Now, Jennifer will talk a little bit more about a prognostic ability to predict plant functional type composition through the FATES model. Plant functional types are defined through numerous traits, vegetation traits, and relationships among those traits. And so most of those are specified in the model parameter file. And I'll talk a little bit more in a second about crop types, so crop functional types as well. So just examples, a couple of examples here on the bottom of where these PFTs exist. So PFT number 2 is boreal needle-leaf evergreen tree type. And so we can see where if you're running ELM kind of with prescribed plant functional types, most of those are obviously going to be in northern Canada or Siberia. And we can see the kind of percentage in each grid cell there. And so there may be up to 100% of this type, there may be less than that, in which case there would also be additional plant functional types in that particular grid cell. And then similarly on the right, PFT4, which is tropical broadleaf evergreen. So most of the rainforest areas in Brazil, Africa, Southeast Asia can be seen there. Each plant functional type occupies a space in the vegetation canopy. And so we have on the bottom left here, for example, leaf scale traits that vary continuously with canopy depth. So one example of that is specific leaf area, basically kind of the thickness of the leaves or the amount of carbon that it takes to make a certain amount of leaf area in the vegetation. Within that, within ELM, sunlit and shaded leaf fractions are assessed every time step. So that tends to be a function of the vegetation itself, but also meteorological conditions and sun angle. And then sort of more here on the bottom right, we see that many output variables in ELM are sensitive to plant functional type traits and parameters. And we've done a number of sensitivity analyses on those, and I won't go into detail, but different plant functional types will see basically maybe different traits impacting the uncertainty or the variation in specific outputs. This one here is gross primary productivity, or amount of carbon that's being taken up by the vegetation. And so, for example, in PFT7, which is a deciduous temperate tree, things like the fine root carbon to nitrogen ratio, this yellow one, tend to matter quite a bit. Things like the fine root leaf allocation ratio, FLNR, or the fraction of leaf nitrogen in visco. Just a little bit about some ongoing improvements in ELM. And so ELM is under active development by quite a few projects and groups, guys. And so there are projects in E3SM and ESS kind of ecosystem projects. There's a kind of the big NG scale or next generation ecosystem experiments in the Arctic and tropics that are developing the model. There's a spruce experiment that's developing a peatland version of ELM. There's Compass, there's urban IFLs developing urban versions and SciDAC projects as well. And so as I mentioned briefly, there's a significant effort within E3SM to build an ultra high resolution version of ELM and be able to implement that on GPUs. And so that's an effort towards continental scale, 1 kilometer resolution. There's also through the subgrid topography structure that I mentioned, incorporation of subgrid radiation calculations for this complex terrain to improve the accuracy of the vegetation and feedbacks there. So there's just an example of some preliminary 1 kilometer simulations that have been performed in this case in the Seward Peninsula in Alaska. So you can see things like snow depth can be resolved at really high resolutions there. ELM crop modeling. So the crop model has been under development recently and can capture various phenological phases of annual crop and perennial grasses that can be quite different from natural vegetation because they're planted and heavily managed. And so there are surface data sets and land use time series that can represent these crop distributions of a number of crops over time. Similar to the natural vegetation, we have carbon and nitrogen phosphorus pools for leaf, livestock, and fine roots, but also for grains as well. And crops are only active in BGC configurations. So 5 types of crops that can be represented: corn, soybean, spring wheat, miscanthus, and switchgrass, representing bioenergy type crops, and then 12 kind of inactive crops. There's been a lot of development within that model to improve the accuracy of prediction through uncertainty quantification and calibration frameworks. So there's a lot of words on this slide, but I did want to say a little bit about how we run ELM in terms of spinning up the model. And so the reason we have to do this is basically to obtain steady state pools that we then use as a starting point for our transient or historical simulations. And so land models generally start with kind of default initial values for all pools, carbon pools, for example, that tend to be very small, or so what we call a cold start. And then in a typical simulation, we assume basically we start in a pre-industrial state, which usually means running 1850 conditions in terms of climate, carbon dioxide, for example, when we think ecosystems were at least at more of a steady state than they are now. And so we call that a spin-up period to equilibrate or reach steady state with those pools. We split that spin-up into 2 phases. And so the first phase is an accelerated phase where we kind of speed up some of the longer lived carbon and vegetation turnover times, which would otherwise might take thousands of years to spin up, especially in kind of cold regions where things don't turn over very quickly. And so we use the and in terms of coupled simulations, typically we first will take some atmospheric outputs, drive the land model in offline mode, so forcing just the land model with data atmosphere, and then perform further spin up in coupled mode to kind of get those feedbacks taken into account. And so after those 2 phases of spin up, then we begin a transient or historical simulation that generally that's what we're using for a lot of the science, in which we turn on time varying atmospheric carbon dioxide concentrations over time, time varying nitrogen and aerosol deposition over time, and also disturbance and land use change inputs. So for example, expansion in cropland over the past 150 years, harvest of forests, and other changes in plant functional types. So ELM specific comp sets and customizations, we'll talk a little bit more about this later. There's really kind of a very large number of potential combinations and options, some of which are covered by defined comp sets or can be set via name list options. And so as a land modeler, I spend a lot of time running what we call I cases, which are offline land forced by either reanalysis or some atmospheric output, which we have saved. And given the relatively small computational expense of the land model, they tend to run much faster. And so we can, perform a global simulation relatively quickly compared to coupled simulations. There's just an example, long name of a comp set, which you can break down into kind of if we're running with a forced atmosphere, kind of DATM, so 1850, DATM would mean these kind of pre-industrial forcing conditions using the data atmosphere. in that particular case, from E3SM version 2. And then the second part of this, kind of the ELM with a percentage sign and then a string of characters which mean different things. And so the CNP, which you'll see, means carbon, nitrogen, phosphorus. And so we can have various combinations of those nutrients turned on and off. We could have carbon only, for example, and then there would just be a C, or carbon, nitrogen. And then RD, the relative demand scheme for nutrient competition, and a CTC, which is the soil biogeochemistry model, converging chocolate cascade. And then the user NLELM can be edited either in the case directory or in a run script, which we'll have some examples on, to change various options. So for example, if we're wanting to change the parameter file, or we're wanting to turn on a disturbance like fire or fertilization, those can be done via the name lists. So just an example here of some of the types of outputs that we see from ELM. So gross primary productivity, which I mentioned briefly before in terms of the vegetation's uptake of carbon. If you watch the animation, you'll see kind of the seasonal pattern of basically photosynthesis as that's going through the northern hemisphere. Summer tends to light up and then is inactive during the winter, whereas in tropical regions, we have a more consistent pattern over the months, but sort of going also varying up and down given the wet and dry seasons in some of those areas. So how do we diagnose and benchmark ELM? So one thing we use is E3SM land model diagnostics, which can give us things like global maps, global line plots, which I'm not showing here, and also tables of global averages or sums of variables like carbon, for example, soil carbon, vegetation carbon. And so the example that I'm showing just shows the results for GPP for two different types of atmospheric forcing. The GSWP3 on the top, which is a commonly used reanalysis product. And then on the bottom, water cycle output from the atmosphere model in E3SM. And so this is a way that we often use these diagnostics to compare two different simulations. And so we can make difference maps of things that may be different between the models. And so we see differences in GPP, for example, over Eastern Brazil and Africa. I've linked some examples there. There's lots of variables that are output from this package. So if you're wanting to see some more variables, you can follow these links. Another tool that we use quite often is called ILAM. And so that's the International Land Model Benchmarking System. And that is designed to compare against observations or observationally based benchmarks. And this is just a partial list here on the left. And so things like biomass, burned area, carbon dioxide, GPP. There's also hydrology, a bunch of related variables. I think there's 3 or 4 more categories that I couldn't fit on the page. And then each column there is a different land surface model. And so this is commonly used, for example, in CMIP6 or other model and comparison studies to look at how models kind of stack up against each other. In this case, now I'm forgetting, I think the blue color means overall kind of better model performance, whereas the oranges and reds relatively poor model performance. And also, we see often in these that the mean model performs better than any one individual model, which is the case for many of these variables. If you can drill down into these analyses, you can click, I think, on each variable and look at specific metrics. And so on the bottom right, so we have a Taylor diagram that will show how these models kind of stack up in that space. And it will provide scores of several different categories. So like the overall bias, kind of a spatial score for how well it's representing spatial patterns, and then an overall score. So again, this is something that's primarily used for a model versus observation comparison. It's a very useful tool as we're doing model development. We implement a new feature in the model, for example, we want to see how that might compare to the last time we ran the model. And so we use it for that quite often. And that was all I had. And so there, if you're wanting to see more about the documentation, I have a link there. And so we will hear more from Tian about river modeling. So typically that, the river model will take runoff as predicted by ELM and route that and predicting river fluxes, and then vegetation dynamics using the FADES model specifically. Jennifer will talk a bit more about that. So I think there is plenty of time for questions if anyone has any. Yeah.
I have a couple of questions. So can we go back to slide
Which one? This one?
Yes, I just want to know like what happens on the southwestern US. Seems like the GDP is always low in that regions.
Desert and dry arid.
Yeah, so that's an interesting, I mean, yeah, a lot of that area is desert. But we do see, when we're kind of zooming in on specific regions, when we're running the model at these kind of lower resolutions, I think this is a 1 degree model. Areas that should have more productivity in higher elevation areas, we're kind of missing a lot of that. And I think that's a resolution issue, because as we push the model towards higher resolutions, we have much more realistic atmospheric forcings at a particular elevation. And this is something that also the topographic units can help to address as well.
Because I'm using the ELM SOC output, I see just in that region, the SOC is also quite low, especially at that regions.
Yeah.
And another is like, can you explain more about like why we have that 4 different pores in the soil? And what's your relation like? For example, I think in each of these 4 we have carbon. So if I want to, so what's going to be the total carbon at this column? We just need to add them all together, or using the last one, the soil pore.
Yeah, so the total soil carbon would be, I guess, the sum over all of these pools. And these are each of these are represented in each layer down to layer 10. And so the model does track that total as one of its default outputs. I think it's the total SOMC, but it's in that, when it's generating that history output, it's doing that kind of weighted sum over all the layers. But given, those decomposition rates are decreasing with depth, we do see a lot of that soil is quite deep, or a lot of that carbon is quite deep in the soil layers. Yes.
I have a question about the model spin up. In the model spin up, did you run the ELM alone, or did you run the E3SM couple model to spin up?
Okay, so yeah, it can be done. So typically, it's a multi-step process, right? So if we're running the model just offline, if our goal is to run an offline transient simulation, we'll do these 2 phases of spin up with typically with reanalysis atmospheric data, right? And then we'll use that as a starting point for the transient simulation. If we're doing a coupled simulation, then there's some additional work that we have to do. So we still do these offline experiments forced with atmospheric model output. But then we need to do another phase of spin up typically, because there's coupling, land atmosphere coupling that we're not taking into account when we're just running offline. And so we'll run typically a couple hundred years of spin up to further equilibrate those pools before we launch into the transient coupled simulations.
So it seems like that even though we won the ERM alone, we need more than 100 years to spin out.
Yeah, so right, I put the numbers of years. So this example is actually quite a bit less than we typically do. And so the accelerated phase, and if you follow the link to the paper, I think it recommends 600 years. With some improvements, I think we can do it typically in about 200 to 250 years. in the accelerated phase, and then we typically need at least another couple of 100 years in that second phase of spin up. So on the order of 500-ish years total. So yeah, that's why, we try to do a lot of this in the offline mode, which is much faster. Yeah.
Nice talk. I have a question about crop modeling and the phase modeling. You mentioned that the crop modeling is still like under development. So how the phase model deal with crops currently? So is that like the CIM 4.5 just put the crop like some parameterizations as C3 or C4 grass, something like that?
Yeah, so the old way of modeling crops was just kind of to treat it as two different types of grassland, and then it would kind of sit on the same land unit as the natural vegetation. So now crops have their own land unit, and so those land units can grow or shrink over time. And I'll let Jennifer answer the question about how that interacts with fates. I think that's.
I guess,
Yeah.
yeah, now I'll give you a quick answer, but for right now, Fates is not really doing crops yet. We still rely on the ELM default land model to do crops. The crops is coming into Fates eventually into the future, so you could choose either one if you want to run crops and Fates or crop and regular ELM. But right now, we're only using the crop modeling in ELM because it's a little bit more advanced since it has its own crop functional types, crop land unit types, more of these perennial crops, more of these bioenergy crops. So I hope that kind of answers it.
Thank you.
Yeah.
Hey, Dan, thanks for the talk. So the model is simulated in a 1D column. I know that's good for computational efficiency. How is that for like realistic representation? Is that like an area we can improve in the simulation, or do we feel like that's a pretty good representation of land?
Yeah, and so that's a big question as we push the model towards higher and higher resolutions, right? I think it becomes more and more important to think about these interactions between grid cells, especially in terms of the hydrology. I know Gautenbisch and others are working on trying to implement that. Some representation of these flows. We can also do some of this with subgrid representation of flows. For example, between columns within a grid cell or topographic units within a grid cell. So that's significantly less challenging from the standpoint of code architecture. So implementing actual flow between grid cells is requires a lot of reworking of the code because, for example, it's using just kind of a round robin distribution of grid cells onto processors, not really caring about where they are spatially. And obviously that doesn't work once you start to consider communication, right?
I guess quick follow-up. I know like historically we represented the model as like a big leaf model. Have we moved away from that yet? I know there was like plans to kind of represent differently. Is it still a big leaf model?
Yeah, I mean, so it has this sunlit shade representation and this kind of integrated canopy, but it's not explicit, at least in these default versions we're running, right? It's not explicitly representing multiple canopy layers. And so that's something I think that, is a strong push of Fates. So, if you're more interested in more maybe realistic representation of canopy layers and competition and size classes, for example, that you would probably want to experiment more with Fates.
Any other questions? No? Not, maybe we'll take I think we're ahead of schedule. So maybe we'll take a 5-minute stretch break, use the bathroom, and if you can be back.
Yeah, keep going. So the river has its own component, Mozart, and directly talk to the coupler. And its job is to, as Dan pointed out, is to route the runoff generated by the land model, ELM, and route it through the river network and send it to the ocean as a freshwater input. Right-hand side is a process layout or computational cost of all the components in a coupled system in E3SM V1. I think V2 has a similar layout. As you can see, the highlighted ROF is the river components only takes a tiny bit of computational resources in the whole system. That's because the river model is a 1D model. It's relatively cheap, like the land model is doesn't.
Progress.
Sorry. It's okay.
Yeah.
All right, okay, let's keep going. All right, so the river model has a name. It's called the Model for Scale Adaptive River Transport Mozart. It's been developed about more than 10 years ago by Holm Lee in 2013. So Mozart, so this slide shows you how we represent the river network or river process in Mozart. So from the top left, you can see that's a natural river system. The concept is to divide the natural river system into river segments. And the river segment will have some major components like a main channel across this computational unit. It can be either a subcatchment or a gristle, lat-long-based gristle, or a unstructured mesh gristle. So it will have a main channel connecting the downstream and upstream, downstream gristles or computational units. And it has tributaries within this subcatchment, like this. And it also has a hill slope process, which like route the water from the hill slope to the tributary and then enter into the main channel. So that's why the conceptualized river segment down below here is how this system is represented in Mozart. It also split the whole computational unit into 3 parts. It has hill slope, subnetwork, and channel routing components. The components, the 3 components within this computational units are represented by different numerical schemes. Like the hill slope process can be represented by the kinematic wave, which is an approximate of the shallow water equation. It assumes the water is steady and uniform. For the tributary flow, the user can choose whether to use the kinematic wave or diffusion wave, which has a better representation of the shallow water equation, allowing you to use the non-uniform flow. In this case, you can simulate the backwater effect if you have a higher water elevation at the downstream location. You can push this wave back to the upstream location. For the main channel, it also has 2 options, the kinematic or diffusion wave. And up here is how this component or computational unit is being represented in the lat-long-based gristle. So you can see that the catchment or watershed or basin has been split into grids. And grids are connected by the river channel with an 8-direction flow direction algorithm. So you have basically that's how the gristle is connected to their neighboring gristles. So let's talk about input of the Mozart model. So the input basically is quite simple. It's just a runoff from the ELM or from other data product. So the Mozart itself allows you to run in a unique concept that only the river model is activated. You can also run it in an I case, like Dan just explained, which ELM and Mozart are active. Or you can, of course, it's part of the coupled system. All you need is the runoff forcing that will be entering the Mozart as an input. So the runoff forcing has 2 parts, surface runoff and subsurface. The surface runoff will directly entering the hill slope process, but subsurface will go to the tributary and then to the main channel. The parameters used by the Mozart as input, here I have a link to the technical guide, we just merged into the E3SM master, where you can find the parameters used by the Mozart. Basically, there are some flow direction information you need, and geometry of the river channel, or the river channel for the main channel or for the tributary channels, and also the roughness of the riverbed as a Manning's coefficient. So you can find this information in the technical guide. And right-hand side is an example for the river network. We have different representation for the river networks. It's not has to be a lat-long based using the A-direction algorithm. You can also choose to use the unstructured mesh, like showing here, right? It's the MPass mesh, which we developed in a separate project called ICON. So in this project, we trying to use a unified mesh to cover the whole global surface. So that the land, river, and ocean will use the same type of unstructured mesh. So as you can see that no matter what kind of mesh you give to Mozart, it can route it for you. Since we don't have a practicum for the Mozart river model itself, so I just quickly show you some outputs of the Mozart. So the standard output files is like will look like this. So you will have a chance to go to the output directory and see these files from the Mozart model. Maybe it's too small for the screen, but you can see that it has a case name followed by the component, which is Mozart. And the default history file is H0, and the user is able to define the different kind of history file by their frequency or what kind of variables you need. You can, so the default is the monthly output, but you can change it in the name list so that you can get a daily or even higher frequency output, and followed by the time, that's year and month. And the right-hand side is one of the a few important variables we are interested in. So here I'm showing you the stream flow discharge, which is the main product of the Mozart. So here I'm just displaying the first month of this output. It's the monthly average stream flow. You can see that the main river system of the global river system is displayed here. And this is another output. This is the discharge to the ocean. And this is where ocean gets the freshwater input. But maybe it's very hard to see from here. So the zoom in, you can see that if we look into the West Coast, you can see their major river output, or as an input for the ocean. That's Columbia River here, and Colorado River here, and Bay Area is here. So these are the major river inputs. So after you get the output of the Mozart, we need to do diagnostics as well, and also evaluation benchmarking. So in the recently published Zhou et al. E3SM DIAX 2.7, I believe, we have implemented a diagnostic tool for Mozart that allows you to evaluate the annual stream flow discharge. So here, I'm just showing you the plots it can generate. The scatter plot here is a annual stream flow scatter plot against the observation. And in the middle is the seasonality, and the different color shows you that peak flow month, so that you can see that where you get the seasonality right, or comparing to the observation. I believe the lower one is the observation and upper one is simulation. And we also have this mean annual stream flow map. That's each, so these dots are gauge locations user can define. So it involves a process called georeferencing, because the observed stream flow is usually provided by the gauge and with a lat-long, precise lat-long, but that lat-long may not fit into the grid cell of the river you are simulating. So there's a process to move these gauge location to the right river segment so that you are comparing apple to apple. So this is an evaluation for general purposes at the annual time scale, but as a hydrologist, you may think it's not good enough. So I also developed a separate tool. Hopefully in the future, it can be integrated into E3SM DIACs as a future release. So this tool allows you to investigate the gauge separately. So here is an example from this V3 historical simulation. And here you will get a map like this. And each dots represent a gauge location, and the color shows you the goodness of fit of the simulation. And blue shows is better, and red is bad, and the black is very bad actually. It's defined by the Nash sective efficiency, so NSE here. So usually is the one means perfect match. A negative one is usually considered as worse, but it can be negative, smaller than -1. So that's black. So if we click into one of these dots, you can see the stream flow comparison between the E3SM, which is blue, and the observation here. This is a seasonality comparison. Along with it, there are a bunch of other matrix. So this is this. Oh. So as I mentioned, Mozart can be also forced by other runoff. So this is another results by a better simulation results, because this runoff is calibrated runoff, and you can see that it matches much better in this case. Okay, so I just talked about the Mozart mostly as a part of the coupled system. So the main job is the route to the fresh water. It's a natural process, but actually a lot of things are happening with the river processes, like the human impact or some other physical processes like inundation, flood inundation, or interactions between river and land model. So we have developed a bunch of additional features based on the Mozart natural system model. Here I'm listing a few. Some of them are, is this okay? Okay. Some of them are funded by the E3SM project, but some of them are funded by some other projects. We call it ecosystem projects. So as you can see that we have V1, E3SM V1 mostly focusing on natural river processes, and V2, V3 focusing on the features including water management and inundation and irrigation between the river and land. And ecosystem projects, as I mentioned, we have developed this unstructured MPass unified mesh. We also have different two-way coupling happening, like river land two-way coupling and land ocean and river ocean two-way coupling, and also some urban representation and hydropower and so forth. So following there are a few slides just to quickly showcase these capabilities. So the first one is the water management. So it allows you to represent the reservoir and dams in the river system. You will have the location of the reservoir, and that can provide the water supply to the downstream result for irrigation. It also has a regulation scheme for dams, so that you will have the opportunity to change them based on the dam functionality, whether it's a flood control dam or irrigation dam. So that will change the seasonality of the stream flow. So here is an example showcase that after we implement this, it will improve the performance of the stream flow prediction. Inundation is a storage along the channel. It's a floodplain. So after you turn on this feature, the water in the channel is allowed to overflow to the floodplain so that you can simulate the floodplain inundation as a fraction of the land. So this is then two studies. One is the original study done in Amazon basin. The right-hand side is a global application. So this is a comparison between observation and satellite observation and simulation in terms of the floodplain fraction. We also have a heat to simulate the stream temperature. So here is the governing equation, which takes the energy terms as an input, and also the heat flux from upstream and tributaries. And that can change the water temperature, but this is an offline feature. That means you cannot use it in a coupled system because it takes the input from the administrative model, but it didn't guarantee the energy balance in a whole coupled system. It can only be used as an offline feature. We also have a sediment transport. It couples the E.R.M. soil erosion scheme developed by Tian et al. 2018. Take the soil erosion as an input to Mozart sediment. That Mozart sediment can route the sediment transport as a suspended sediment to downstream. We also have two-way irrigation coupling, where you have a chance to take the water out from the river system and put it back into the land. It's not just a one-way process anymore, because before it's just the river taking the runoff from land one way, and now we can put the river water back to the land system. Yeah, I think that's the final slide of my talk, and thanks for your attention. I'm ready for questions.
Thanks for your talk. Could you elaborate more on, since ELM is not spatially explicit, but Mozart is, can you just talk more about how, yeah, they're coupled and what time step and yeah, how does the runoff kind of spatially make it into the.
Right. The mismatch between, in terms of the time and the spatial mismatch between land and river is handled by the coupler. So no matter what kind of resolution ELM is using, it can remap to the river network and as an input so that it can sit on the land long or whatever grid system you're using for the river model. But if you are trying to use this two-way coupled system, a two-way irrigation, like for example here, we have to make sure that the river and land are sitting on the exact same resolution grid so that the flux are one-to-one match to each other. We only need to handle the time step difference for the coupler. But yeah, I don't know if that answers your question. Yeah.
So great talk, thank you. I was wondering about Mozart heat. Has anybody looked at the heat coming out of Arctic rivers and if it might impact scale?
Yeah, that's a great question. So we don't have a phase change for Mozart heat, and Mozart heat allows negative temperature. So it only guarantees that the energy is balanced by using this relatively simple governing equation. As you can see that it doesn't have, it allows you to route the river with negative temperature. It doesn't change, shift it to ice. So I would say it's not very practical or recommended to use it in the Arctic region for now. But we are in different projects. We are exploring ways to implement the ice process into this. So, but that will, yeah, that's some future development. Yeah. Yeah, sure.
Can you talk about what the process might be to run this in a single basin, not multiple?
Oh, yes, we do have this kind of a feature. So as you can see, for example, in this example, we only do a simulation for the Susquehanna River Basin. And it's a unique setup. I think, I'm not sure if it's in the E3SM master branch, you can use this, but for the ICOM, we have a dedicated branch and that allows us to route single basin. But I believe in the master, we have a concept that allows the CONUS, only CONUS at NLDAS resolution, 1/8 degree for NLDAS, for the CONUS region. only, yeah. I think these can be customized. It's not that, yeah. Yeah.
So I just want to know, is there any quick way to figure out the river mouse, which entering the ocean?
In the model,
Just want to know the location of it, like which person.
yeah, based on the parameter file of Mozart, you are able to find out it's been labeled by different flags.
We have a mesh for that.
Yeah. Yeah, you said you have a mesh already?
So, so you're saying like we already have a mesh for the river location of the river mouse in the.
Yes,
parameter
in the parameter file. Yeah.
Yeah, Mozart heat, I was wondering if you had actually enough observations to validate the model.
So this is an validation actually in that paper. So as you can see, this blue dots are observation and the red ones are simulated, I believe. But you can see that in Colorado, below Hoover Dam, it's doing not that well. That's because the dam, the reservoir has a cooling effect and it will flatten the temperature. So this paper also discussed after turn on the water management, after you implement the dam and reservoir, it will improve this performance. Yeah.
Thanks for the talk. Maybe a naive question to ask. Is the change of river channels considered an important feature?
It's not considered, but I mean,
since this is one component for the Earth system model, which runs for centuries, I just wonder whether.
Yeah. Yeah, river geomorphology, I think it's currently not a consideration, I think, but it definitely will have I mean, it is interesting to think about. I mean, for even longer simulation, I think the paleo hydrology that's usually looking into this so that you will have an updated river network to simulate when the time advances. But currently, I think we are just using a fixed river route output because if you change that will change a lot of things, and the ocean will get different input from the river. But we do think in one of the projects we do think we probably need to incorporate the delta into the system. For now, it's just the one grid cell entering the ocean, but in reality, like Yukon Basin or Mississippi, it has a large delta. We can, when we advance into a finer resolution, it's not ideal to just use one grid cell to represent the river mouth. So that's something we're considering to represent the delta. Yeah. Sure.
Well, I've got two questions. The first one was interacting with biospheres. So if there was, say, glacial melt, or if that was simulated, does it get routed through the river routing scheme in MISA?
Oh, you mean sea ice?
Well, sorry, land-based ice rather than sea ice.
Land ice, I think that's it provides, I believe that provides the input to Mozart, but Mozart doesn't route it. It just directly send it to the river mouth. Yeah, that's my understanding.
Then the second question was kind of following up, I think, from the question before. A lot of terrestrial water is pretty heavily influenced by what humanity's doing, damming or those kind of things. And so presumably this is environmental flows without, you know, human intervention with damming or whatever. How do you validate the environmental flows that Mozaart's trying to reproduce with reality, which is way more complicated?
Yes, we did evaluate that in different studies, but they're mostly regional studies. And I would say these evaluations are not based on coupled system. They usually take a very good well-calibrated runoff as the input and then evaluate the impact of the dams and reservoirs. But for a coupled system, I think we have to, yeah, since this feature, the water management feature is not a default feature turned on in in current E3SM. So I think it's not being evaluated by E3SM direct, but yeah. Yeah, that's. Sure.
Is there any sort of nutrient transport?
Yeah, it's been developed. I think it's under development. So I did I include that somewhere here? We do have a Mozart BGC, it's under development, but it's not available right now. Yeah.
Thank you, Ken.
Thanks.
And next up will be Jennifer Holm talking about the fates.
Hello, everybody. Yeah, I'm Jennifer Holm. I'm here at Berkeley Lab, and I'll be talking about the fates model, the functionally assembled terrestrial ecosystem simulator. And there's a very, very, very big fates team of a lot of people that work on development and testing of this. And Dan did a great primer really talking about the ELM land surface model. And this is just another additional model that can come in to kind of substitute the vegetation component, so the roots and the above ground vegetation. And right now it's not the default kind of land model, but you could substitute it in and out. And we're hoping that it could eventually become the default land model. And it actually is coupled to a lot of other system models. So not just E3SM, it's also in CESM and the Norway Earth system model. So because it is its own separate land model, it also has its own GitHub repo as well. So here's just some useful links where you could go to the GitHub for fates, and then that is linked into E3SM as an external submodel. And then fates also has its own very, very detailed technical doc that's very long and will explain many of the things that I won't have time to talk about. Okay, so how is fates distinguished from the native ELM? And these are the main things. It's a cohort-based vegetation demographic model. And I'll say what kind of demographics are. That's one of the key words. And then this last phrase, it does dynamic biogeography. So instead of static vegetation, the plant functional types being static in their grid cells and in their locations around the world, we can now kind of look at future shifts and change of vegetation as it's changing with climate change and warming or droughts, of where there might be shrub encroachment or different places, or altitude or elevation encroachment. So that's kind of one of the major things that fates brings in, is this dynamic prognostic biogeography. Okay, so yeah, a little history and evolution of where we are in land surface modeling. So you guys know, of course, like earlier in the 70s and 80s, it really just kind of did these energy balance fluxes. And eventually over time, we've added on all these additional components where it's like, hey, we need to also look at soil moisture. We need to look at carbon cycling. Land use change is probably important. Nutrients are important. And eventually we're where we are now, where I've circled, and bringing in this demographic vegetation. So ELM is kind of this representation of this single canopy model that is static, that is unstructured, but it does have a variation within that single canopy of sunlit and shaded canopy. And fates is everything else. So fates now does introduce a little bit of 2D, at least on the above ground, but not on the below ground. The below ground is still a 1D model, but up in this above ground component, we now have a little bit of 2D and canopy width, canopy depth. You get a little bit of 2D with where the patches and the cohorts are, and also seed dispersal going across grids. And because of this we've introduced this disturbance and this change in disturbance over time, you get this successional change in vegetation where it has kind of this, there's a disturbance, you get a young vegetation stand, kind of grows up into this old stand. And so everywhere on the planet, there's mosaics of these disturbances and mosaics of these different canopy structures. Okay, so what's the kind of the breakdown of a grid cell, where on ELM, that's what it is, kind of over here on the left, where in a grid cell, you'll get these different plant functional tiling. So different types of trees and grasses or bare ground that Dan kind of showed. And now we break that up to where we have these patches on these time since disturbance, and you can now track vegetation age or forest age for the first time. So after a disturbance, we'll have this mosaic of different ages of the forest. And that's what this time since disturbance tiling is. And then remember on that time since disturbance tiling, we now even have an extra level of complexity, and we have different cohorts of trees now in different sizes and by different plant functional types. So on a young patch, you will have small trees. And then as your patches get older and older and older, the trees will grow at different sizes, different canopy widths. They're competing for different light, heterogeneity, water, soil nutrients. So yeah, so it's just this extra added layer of complexity of age and size distribution. Just kind of one more schematic, kind of breaking down exactly what I've already said, maybe in another way to think about it. So again, static vegetation, single canopy. We now have multiple canopies. And kind of in these gray boxes, these are all the kind of new features and new scientific questions you could do with fates. So if you have a multi-structured canopy, you now have this heterogeneity in your light environment. You have different size structure of the forest. You could look at interesting questions about plant competition for light, water, nutrients. These cohorts are, yeah, I already talked about the cohorts and the patches. You could look at questions about recovery after a disturbance, so dynamic succession and what happens after fire or land use change. And then this last box is this main kind of really cool thing. Because of all these features, this plant distribution on the globe will now emerge prognostically based on all these traits and this competition and disturbance. Okay, so yeah, so I mentioned this at the beginning, fates is a submodel, so it must be associated with a host land model, and that's why we have ELM fates. There's also CLM fates, there's also Norway fates. So yeah, so fates is everything kind of within this green blob and little light brown blob around the vegetation canopy and the roots. And then ELM, the host land model, does everything else. So ELM will still do the energy balancing, the soil carbon, soil biogeography, you know, everything in the subsurface, hydrology, land use change. And then that passes it over now to this 2D representation where you have all this different structure of the forest, different turnover rates. This is if you guys kind of want to see exactly what's passed back and forth, I find this a little bit helpful to remind me, okay, what's coming from ELM, the host land model? What are the exact things that are being transitioned back and forth to fates? So this is kind of a nice, I don't know, just schematic if you ever want to come back to this of soil, water, radiation, you know, these different things go over to fates, and then they do everything in the canopy and water stress on the plants, the photosynthesis, respiration, the growth, allocation, mortality, and then all those litter fluxes, changes in albedo, changes in canopy resistance, then gets passed back to the ELM model. So again, it's just substituting in kind of all these new ways to look at vegetation change. And then, kind of breaking down what Dan showed before of these nested hierarchies. ELM is here on the right where you have, I left off topographic units, but it's grid cell topographic units, land unit. And then now fates site will sit at this column level. And then the level below that where ELM sits at the PFT level is now where we have our patches, and then one more level of hierarchy below that is our cohorts. So Dan showed some really good stuff at how ELM is getting now higher scale resolution, is 1 kilometer grids. Our site is even more higher resolution than that. It's at the 1 hectare scale. So 1 hectare is like what, a 0.1 kilometer. So we could get very fine scale at the hectare scale, and then within that, patches of different age, and then cohorts of different size. So it just brings in more heterogeneity, more hierarchy. Okay, so just like the vegetation and the native ELM fates also does all the same processes where it will still have soil biogeochemistry, it will still have plant hydraulics, but since the vegetation is different, there is a little bit of slight differences in either like the nutrient cycling or the plant hydraulics, because now you have to deal with cohorts of different sizes and allocation of that carbon or nutrients into slightly different pools. So here's just two schematics of showing the paper for the nutrient cycling in fades, and then the papers for the plant hydraulics. In fades hydro. And then, fades also does wildfire dynamics. So ELM also has a wildfire model. Fades also has a wildfire model too, that's based on the Spitfire model, where you can see where it brings in the weather as an input that will then help tell the initiation or the ignition data set. And then all that goes into the fire spread model, where you look at different changes in your fuel state based on your vegetation, your fuel combustion, the rate of spread. And all that eventually will give the amount of burnt area. And then all that will go into the fire impact, the green box, which is everything up for your PFTs. So based on how tall you are, how much canopy you have, that changes your crown scourge, then that changes your mortality. And all that is kind of fed back in and through this loop to the fire impact leads to mortality, that then leads to also more fire spread. So, okay, I'm going to just quickly talk about some more kind of specific processes that are a little bit more unique to fades. Like these other kind of three that I was saying, there's still carbon or CNP cycling, there's still plant hydraulics, there still is wildfire. But some of these things about kind of allometry, dynamic recruitment, mortality, trait plasticity, canopy heterogeneity are things that are a little unique to fades. And each of them can almost be their own talk. So I'm just kind of quickly go through them to introduce them. So now, since we do have different sizes of trees, we do allocation of carbon. Oops, I don't know what that is, go away. We can do allocation of carbon kind of through these different plant pools, through your roots, your stems, your branches, your leaves, and all this is based on the idea of allometry. So we have these allometric equations, and then your carbon and your nutrients are put into your different pools. And so, the allometry is everything that really governs your proportionality of where your carbon goes. And the figure at the bottom is just kind of an example of a diameter to height allometry. Now that we do know the diameter of trees, the height of trees, you can figure out where that carbon allocation goes based on these allometric curves. We have a lot of different types of mechanistic plant mortality. So this kind of wheel is showing all these different types of ways that plants can now die. And ELM fades, it's just a static 2% mortality everywhere on the globe for every plant functional type. And we know in reality, like that's not true, that plants will die of either cold stress or hydraulic failure if they're in arid situations, or carbon starvation, or just tree fall or fire. So each of these things in this wheel have their own mechanistic equations to account for that. And then there's also crown damage. So it's just a partial loss of the crown, but not a complete canopy depth or death. And then there's also mortality that is age and size dependent, which is this paper by Needham, where she showed the different changes in above ground biomass based on, if it's age dependent mortality or size dependent mortality. We also have very, very dynamic reproduction and recruitment now. So these are schematics from two different papers and two different figures, two different papers, where the amount of carbon that goes into the seed flux is a fraction of NPP, and the recruitment scheme is based on this environmental sensitivity of your location. So what the soil moisture is, what the light regime is, that will then all lead into the amount of seedling emergence that happens and the amount of seedling death, and then eventually the recruitment. So these are kind of the dynamic vegetation parts, the dynamic mortality, dynamic recruitment, dynamic growth that kind of sets fades apart from a native land model. And then there's different ways that we could do this kind of canopy heterogeneity. So like I was mentioning before, we do have different canopy levels, and that's what this figure on the top is showing. So an upper canopy, a lower canopy, and you have these three different choices that you could pick in the model of how you would like to represent disturbance and how you would like to represent that trees get promoted and demoted into different parts of the canopy. So you could do it in the PPA stands for the perfect plasticity approximation. So you could either do it on this, that plants have this pure plasticity, or it's kind of this mixed level, or kind of Ed is back to the ecosystem demography model of when you create a new patch based on your disturbance. So it's just kind of different ways to look at this canopy competition and the ways that it will create new patches. Okay, and other stuff that's really cool is that there's a lot of different traits that go into making up all these different plant functional types. And in Fates, you could extend the plant functional types really by however many you want based on traits. Since it's a trait-enabled model, it's data-driven. This is a study by Marcos Longo where he ingested all these different traits from these different input data sets like Tri and Talo and different tropical traits. And then he was able to do a cluster analysis to then really kind of pick out the plant functional types that are based on different soil moisture traits or drought traits, or if you're early successional or late successional. And we have the flexibility to really kind of change our parameter file to make it as trait driven as you would like based on data. Okay, a little bit of background, just kind of where we're going on global simulations. So Fates is also tested a lot at individual sites since it's so detailed and you can really match it to observations. And it's tested a lot of regional places like in the Amazon, but we also have ongoing global simulations. And, oh, sorry, I know this is a lot. But to be able to test it in these different global modes, we also introduced these new levels of complexities that you could change the model to do. Again, to answer different science questions and to help with global calibration. So at this top level, you could run Fates in what's called just a satellite phenology mode, which is almost identical to the ELM satellite phenology mode. So that's almost ranking in a one-to-one comparison to the static ELM model. If you just want to do a sanity check, how does Fates compare to static single canopy ELM? You could run it in that mode. And then as we're going down this list, it's turning on levels of complexity. So you could choose to actually keep it a fixed biogeography where you're telling the plants where to live and it has no competition, but it does bring in a little bit of still height dynamics. And you can kind of look at those differences. And then each one is kind of adding on, well, now we want to add in competition. Well, now we want to add on the fully dynamic prognostic biogeography of Fates. So each one of these are just turning on and off these features to test different things in a global setting. And then this table kind of shows like, what exactly are these different variables we could calibrate in each of these different steps to get us all the way down to that bottom level where it's a fully dynamic Fates, fully prognostic Fates in a global setting, fully coupled in E3SM. And then here's just some initial results to show. This first was the sanity check I was talking about, where we're comparing Fates and satellite phenology mode to ELM and satellite phenology mode and looking at the outputs of evapotranspiration and the outputs of GPP. And we're seeing that Fates does a pretty good job when compared to the native ELM and also when compared to FluxCom, which is good. And then just like how you could test any of the land service models in ILAM, we have tests of Fates in all these different configurations. So each of these columns are basically kind of different levels of these rows, different levels of like what happens if we turn on or off biogeography or on or off competition. How well does it do? And this is still kind of under development of improving each of these colors, but we're on our way to kind of testing each of these capabilities in global runs of Fates. Okay, so I'm near the end, just kind of wanted to remind everybody that, you know, again, FATES has its own repository that's hosted by, what this NGT is the NG Tropics project. So they're the ones that host the repository, do the pull requests, do all the code maintenance, and then also we do the integration into E3SM. And then this is where FATES lives in E3SM. So if you start all the way up at the head of E3SM, of course, there's SEAM and then components. And then going into the components, you have to go all the way through to ELM and then in the source code. And then all the way through there's the little external models. And that's where FATES sits. Since, like I said, it's kind of this different external model you could substitute in and out. And this is all these different features I was kind of talking about. You could turn them on or off in the name list option. So we're hoping that that's a pretty easy way. And these are the options to go back and look at to use. If you want to turn on fire, if you want to turn on logging, plant hydraulics, turn on the nutrient code on and off. And this is the flag to do it. A couple of these other kind of different modes that I was talking about, like the prescribed phenology mode. Yep. There's a link on there to the wiki. The wiki has a whole bunch of information. I think that's my last slide. Yeah, there's a whole bunch of information on here about this is where you get the parameter file, how to adjust the parameter file. FATES has its own tutorial itself, which is like 3 days long. And there's links to FATES tutorial just about that with slides and everything that you want to know of how to use it and run it. So I hope this was helpful. I think that's my last slide, yeah. Yeah.
Great talk. Do you have a sense of how much better FATES performs in high latitude vegetation simulations? Because there are like some processes where if you don't get the height of shrubs in places like Alaska or Canada or Siberia right, you might affect the energy balance strongly because of the albedo consideration. So does FATES improve on that? Or?
That's a great question. We are now just only in the past year starting to run FATES in Arctic systems. So that's the brand new project like NG Arctic is now picking up FATES. And we need it almost just for the shrubification thing too. So if as shrubs are kind of moving into different places, FATES is really the model to be able to look at that. And you're right, and then the different heights and the snow dynamic. So I don't have the answer to your question yet of if it's better, but we are starting to run it in the Arctic. We are starting to do some of these new processes, and we need to still benchmark it and look at it. So I might come talk to you later once we have these results. I'll be like, are they better? I would love to know. Yeah.